Yes, students, let's come back to the point where we have left. So in last lecture, we have seen about introduction and the basic foundation building blocks that are required for understanding finite automata. Uh, the finite automata is being represented by five tuple structure, and that five tuple structure contains a set of finite states, an input alphabet, a transition function, a start state, and a final or accepting states. Okay, so this is being defined into the five tuple structure. So every finite automata, whatever you draw, is being defined by these five tuple structures. So the important terms are this only: Q, sigma, delta, Q0, and F. And no doubt, F is being part of Q only. So either you can define it separately or likewise, but Q0 and F are the part of Q only. Okay, so let us try to understand this by this particular way. Yes, so let us try to understand this by this particular way. So you have got finite automata now. You have got a finite automata. And for a finite automata, as per last lecture's discussion, we have understood the basis. Okay. So what are the basis for this finite automata? You need to work with graph. Okay. You need to work with graph, and this graph must be what? Directed and weighted. Okay, this graph must be directed and weighted. And as far as implementation is concerned, you must be able to understand the graph representation using adjacency matrix or adjacency list. You can represent graph using these two techniques. Okay, and this we know that this graph is represented by G in bracket V comma E. So we understand that V is vertices, A are the edges. So the basis is graph. Okay, so this finite automata is having this one. Okay, so the next important thing with this is what input it takes. Okay, so you need to understand the input also, right? And the input is RE. RE stands for regular expression. Okay, so please try to understand the language which is defined by with the help of RE is regular language. Okay, so the language which is defined by the regular expression is called as regular uh, language. This is important. Okay, and if the language is being accepted by finite automata, or say for example, a regular expression is accepted by finite automata, then for this regular language, the finite automata is also useful, right? So finite automata is also accepted a regular expression, and it is for regular language. So these are what? These are the basis. Okay, so next important thing is that once you understand this basis, right, so we will just try to extend this particular all these basics part to one more level, that we have seen the graph. Then the important thing which comes in front of us is called as transition function. Okay, so this is also important point, right? And we understand that the transition function is being referred as delta. It takes state and input. Okay, it takes state and input, and this transition function returns the state number, where state. Okay, so means, say for example, you have certain representation of a graph which says that there is a vi vertex, and from vi you are reaching to vj with a particular input. Then this transition function is being written as delta vi comma a and the result of vi comma a is vj. Okay, so the resultant is vj. So you try to understand this particular example so that you can proceed further. Is it okay? So this is important. Now let us come back to this particular point. Okay, so now you have got a finite automata FA, finite automata, and this finite automata is represented by five tuple structure. What are they? First is Q. Okay, then what is next? See, first is Q, then sigma. Right. So what you have got is first is Q, then you have got sigma, then uh, you have got a delta q0 and f. So f. So let us try to understand these terms now. Okay. Let us try to get an example. So the input for us will be, let us try to have an input here. So the input is what we need, a regular expression. So let us try to have a simple regular expression as uh, a, b, and b. So a simple regular expression a, b, b. So means what? You have a language L which is defined over set of symbol A and B such that the regular expression is ABB only. So the words that are generated, W that are generated for using this regular expression is ABB only. Okay, so it has got one occurrence of A and two occurrences of B. Okay, so now how this is being represented? If you start drawing it as per a graph, so we need to write. Okay, this is my zeroth state. Then zero, I'm going with A. This is my one. Okay, this is one. Then I'm going with B. This is two. Then with this, sorry, this again one more B. Sorry, this is B, and this is my accepting state. So at the end, if I start with 0, and at the end what I'm going to get at third, I'm going to get ABB. Okay, so now here if you look at this Q, if you look at this Q is containing 0 comma 1 2 3. Okay, Q is what? Q is a finite states, finite state, right? And this is a set of what? Set of finite states. Got it? See, Q is a set of finite states. Okay, or it's a finite set of states. Okay. Next is here we need to discuss about the next important point, that is called sigma. Now sigma is, since if you look at this language which is based on alphabet A and B. So here input alphabet sigma is containing A and B. Okay, so this talks about sigma talks about input symbols. Okay, then there is a delta. Okay, so delta is what? A transition function. Okay, and this transition function is with respect to every state marked in a set of Q. So means this delta that is called as this delta is called as transition function. Let's write it here. Delta is my transition function. This transition function is applied on every state. So let's work out, say for example, delta of 0. What is input? A is applied on, see this A is applied on 0. So here delta 0 A, and what this gives me? This gives me 1. Okay, next delta 1 comma B, what it gives me? 2. Then delta 2 comma B, what it gives me? 3. Got it. So you have got this. So using a using a transition function. Okay. So here, if I say delta 3 comma question mark, because on 3 you don't have any input symbol, so you don't go anywhere with delta 3. So but here, uh, this third state, that is, if you look at q0, q0 is your 0, which is nothing but start state. Okay, and f is nothing but 3, which is your final or oblique accepting state. Okay, final is or accepting state. So q0 is 0, f is your 3, and this is the transition function. Okay, if you look at this q0, you will find that q0 is what? Is part of q. F3, F is what? F is part of Q. So if you look at 0 and 3, so here is 0, here is 3. So 0 and 3 both are part of Q. So I hope you understand this. So a set of finite state is called as Q. An input alphabet is a sigma. A transition function is delta. A start state is Q0. Q0 is what? Q0 is on in Q only. And a final or accepting state is F, and F is a subset of Q. Okay, so this is how it works. Okay, now here again, if this is your finite automata, in this case, in simple case, yesterday in last lecture only we have seen the properties, right? That you must have one particular age labeled with one particular input alphabet, input symbol, and that age is leaving to a vertex and approaching to the next vertex. Means vi comma vj, you need to understand vi age vj, you need to understand. So this is what exactly the concept is. Okay, so by this you will come to know that this is how a finite automata is represented. Now